Look up. If you can find a place truly dark, a place untouched by the relentless glare of our own civilization, you are staring into the heart of an ancient, impossible promise. That scattered dust of light flung across the blackness is more than just a beautiful sight. It is a map, a summons, an invitation written in fire across the full breadth of the observable universe. It is a siren song that has echoed in our minds since the moment we first recognized ourselves as a species capable of wonder. The dream is older than our cities, more enduring than our empires, and more universal than our gods. It is the dream of the journey out, the deep, instinctual, unshakable conviction that our destiny is not bound to this single, fragile world, but is waiting for us out there in the silent depths. We have whispered this story to our children for generations. We have painted it on cave walls and encoded it in our myths. We have built monumental cathedrals of stone and steel that strain toward the heavens, as if trying to breach the great blue veil that separates us from the cosmos. Every voyage of discovery across the oceans of our own planet was merely a dress rehearsal for this, the final grandest expedition. Our science, our art, our entire technological ascent can be seen as a slow, methodical preparation for the voyage. We built telescopes to sharpen our eyes, turning faint smudges into magnificent swirling islands of 100 billion suns. We learned the language of the cosmos, mathematics, and discovered that the same laws that govern a falling apple also choreograph the waltz of galaxies across eons. We listened. With colossal dishes tuned to the whisper of creation, we eavesdropped on the dying breaths of ancient stars, on the birth cries of new solar systems, hoping to hear a voice, a signal, a confirmation that we are not alone in this boundless auditorium of existence. The silence we received in return did not deter us. It only deepened the mystery, and with it, our resolve. Then, in a historical blink of an eye, we took the first step. We broke the chains of our own gravity. We left the cradle striding first onto our moon, planting a flag not of conquest but of arrival. A statement to the universe that we were at last ready. That small step was a promise to ourselves, a down payment on a future among the starfields. From there, our ambition only grew. We sent emissaries of silicon and gold, our robotic proxies flung into the void on trajectories of breathtaking precision. The Voyager probes carrying the sounds and sights of our world are now silent pilgrims in the interstellar darkness. They are the first lonely messages in a bottle cast into an ocean of unfathomable scale, a testament to our hope, a symbol of our unyielding desire to make contact, to explore, to simply go. We have gazed at the images sent back to us, visions that have redefined our sense of beauty and scale. The pillars of creation, colossal nurseries of gas and dust where new suns ignite like celestial fireworks. The ghostly glow of the Ring Nebula, the beautiful expanding shroud of a star, not unlike our own, showing us a glimpse of our own sun's fate. The Carina Nebula, a turbulent city of stellar titans, a landscape of such chaotic and violent splendor that it feels torn from a forgotten mythology. And beyond our own stellar neighborhood, we see them, the galaxies, countless stupendous, magnificent galaxies, whirlpools of light, serene ellipses of ancient stars, and chaotic collisions of star cities locked in gravitational embrace. Each one a Milky Way in its own right, each one potentially hosting billions of worlds, billions of new possibilities. Our nearest great neighbor Andromeda hangs in our sky as a faint, ethereal smudge, yet we know its true nature. A cosmic continent of 1 trillion stars waiting across the dark. It seems so close a destination beckoning to us. This is the dream in its purest form. A future where our descendants pilot starships through these vistas, where humanity is no longer a species of one world, but a civilization of the galaxy. where we walk on planets orbiting alien suns, breathe atmospheres of a different composition, and witness sights that we today can only struggle to imagine. It is the ultimate narrative of human progress, from the plains of Africa to the star streams of the Perseus Arm. It feels inevitable. It feels like our manifest destiny. But what if it is not? What if the greatest story we have ever told ourselves is just that, a story? What if the promise whispered by the night sky is not a promise at all, but a beautiful, tragic illusion? What if the vast, silent expanse between the stars is not an ocean waiting to be crossed, but a wall, an absolute, impassable and permanent barrier? This is a profoundly uncomfortable thought. It runs counter to everything we want to believe about ourselves, about our potential, about our future. We are a species defined by the overcoming of limits. We conquered the seas, the mountains, the skies of our own planet. We solved diseases, split the atom, unraveled the code of life itself. Surely the stars are just the next grandest challenge on that list. Yet the universe does not care for our stories. It does not bow to our ambition, nor does it grade on effort. It operates on a set of rules, of fundamental laws that are as magnificent as they are unforgiving. And it is within these very rules, the ones that make the cosmos so spectacular, that we may find the fine print of our confinement, the clauses that permanently bind us to our home. The journey we are about to embark on is a different kind of exploration. We will not be traveling to distant stars. Instead, we will journey into the very nature of reality itself. We will investigate a series of profound, interlocking obstacles, each one more formidable than the last. These are not simple technical problems waiting for a clever solution. They are not challenges that can be overcome with more funding or a more powerful rocket engine. These are fundamental aspects of the universe we inhabit and of the fragile biological machines we are. We have identified 7 of these great barriers. 7 separate yet interwoven reasons that suggest the dream of leaving our Milky Way may be precisely that, a dream. These reasons are not pulled from science fiction, but from the hard-won discoveries of our own science. They are found in the equations of Einstein, in the brutal mathematics of rocketry, in the delicate biochemistry of our own cells, and even in the intricate, fragile web of human society itself. The first great barrier is written in the language of light and time. Physics itself, the bedrock of our understanding, has drawn a line in the cosmic sand. We speak of light years so casually as a measure of distance, but this unit hides a terrible truth. It is not just a measure of space, it is a measure of profound, unbreachable separation. The speed of light is not a target to be broken. It is the ultimate speed limit of the cosmos, a law woven into the fabric of space-time. Why has the universe imposed this cosmic speed limit? And what are the staggering, world-breaking consequences of trying to even approach it? The answers reveal a universe far larger and more inaccessible than our imaginations have ever dared to conceive. Then comes the challenge of the vessel itself. The engineering required for an interstellar journey is of a scale so far beyond our current capabilities that it borders on the magical. We imagine sleek, elegant starships gliding through the void, but the reality is something else entirely. A true starship must be more than a vehicle. It must be a self-contained world. It must protect its inhabitants from a vacuum that would boil their blood, from temperatures that would shatter steel, and from a rain of radiation that would shred their very DNA. It must do this not for days or weeks or years, but for centuries, for millennia. It must carry a society across a desert of absolute emptiness, powered by energy sources we have not yet conceived, built from materials we have not yet invented. Can we truly build a machine that can outlast the civilization that launched it? A machine that must function perfectly for longer than the entire recorded history of humankind. Even if we could solve the physics and engineer the ship, we would then face a barrier, far more intimate one we carry within ourselves. our own biology. The human body is not a machine designed for the cosmos. It is a delicate temporary assembly of water and carbon, an artifact of this one planet. Every cell within us is finely tuned to Earth's gravity, its atmosphere, its magnetic field, its 24-hour day. Take that away and the machine begins to fail in startling ways. Our bones dissolve. Our immune systems weaken. Our minds evolve to navigate a terrestrial landscape struggle to comprehend the crushing, featureless emptiness of the interstellar void. What happens to the human organism over generations spent in deep space? What genetic toll would the journey exact? Can a creature born of this world ever truly be adapted for a life between worlds? The problem may not be getting our bodies to the stars, but keeping them from falling apart long before they arrive. Beyond the challenges to our bodies are the challenges to our minds. The psychological burden of such a voyage is almost inconceivable. Imagine leaving Earth and watching it shrink behind you from a blue marble to a bright star to just another anonymous point of light, indistinguishable from a billion others. Then nothing. For 100 generations, your entire reality is the metallic interior of a ship surrounded by a perfect, unchanging blackness, punctuated only by the distant, cold fire of stars that never seem to get any closer. There is no sky, no seasons, no horizon. No tangible link to the billions of years of evolution that shaped the human psyche. This is an isolation so profound it has no terrestrial equivalent. Could any crew, any society endure this existential siege? Could our sanity survive being so completely and irrevocably cut off from the only home our species has ever known? And this leads to perhaps the most complex and overlooked barrier of all, the sociological challenge. An interstellar mission is not a journey of individuals. It is a journey of a civilization in miniature. A society would be born, live, and die entirely within the confines of the ship. What would hold such a society together? The original purpose to reach a distant star would be an abstract legend to those born centuries into the voyage. They would have no memory of Earth, no connection to its cultures, its history, its art. The destination, a place they will never see, would be a religious promise made by long-dead ancestors. How do you maintain purpose, law, and a cohesive culture across dozens of generations in a sealed metal can? The history of humanity is a history of conflict, of schism, of societies breaking apart under pressure. What new and terrifying forms of societal breakdown might occur in the most extreme environment imaginable? The ship might survive the physics of the journey, only to be destroyed by the sociology of its own crew. We must also confront a chilling economic and political reality. The resources required to build and launch a true starship would be staggering, likely demanding the total economic output of the entire planet for a century or more. What civilization would be willing to make such a sacrifice, to pour its entire treasure, its energy, its brightest minds into a project from which no one alive, nor their children, nor their great-grandchildren, will ever see a return? It is a project with a timeline that mocks political cycles and defies all conventional notions of investment. It requires a unity of purpose and a stability of vision across centuries that our species has frankly never demonstrated. Are we even capable of cooperating on the timescale necessary to begin such an odyssey? Finally, we must ask the most fundamental question of all: why go? We tell ourselves it is for the survival of the species, a lifeboat to escape a dying sun or a planetary catastrophe. But is this rational, or is it a romantic justification for a deep-seated, perhaps irrational desire? The universe is not a collection of pristine, empty Earths waiting for us. The overwhelming majority of worlds are likely to be hellish furnaces, frozen wastelands, or toxic nightmares. The sheer astronomical odds of finding a planet that is not just habitable but truly compatible with our complex biology are difficult to overstate. We might cross an impassable gulf of space and time for 1,000 years only to arrive at a destination that is fundamentally lethal to us. Is the greatest risk of all that we might sacrifice everything we have, our entire world, in the pursuit of a new one, only to find that there is no other place in this universe that is truly meant for us? These 7 arguments, the tyranny of physics, the impossibility of the machine, the fragility of our biology, the peril to our minds, the collapse of society, the prohibitive cost, and the profound uncertainty of the destination, form the pillars of our investigation. Each one represents a lock on the door to the stars. To leave the Milky Way, we would need a key for every single one. If even one holds fast, we remain here forever. This exploration is not intended to be an exercise in pessimism. It is not meant to diminish our ambition or to mock our dreams. On the contrary, it is an act of profound appreciation. By understanding the true unyielding scale of the cosmos, by confronting the monumental challenges it presents, we can begin to see our own world and our place within it in a new and extraordinary light. The goal is not to prove that we will fail. The goal is to understand what failure would even mean. Perhaps our destiny is not to conquer the galaxy. Perhaps our destiny is to conquer ourselves, our divisions, our short-sightedness, and to become true wise custodians of the one world we are certain is ours. The story of humanity may not be written across 1,000 star systems. It may be written here in the thin, precious envelope of this atmosphere, on this revolving sphere of rock and water. And perhaps in a universe of such brutal, magnificent indifference, the struggle to build a lasting, intelligent, and compassionate civilization on this one lonely outpost is the most heroic journey of all. The dream of the stars is beautiful, but the reality of our situation may be even more profound. Let us begin. Every star you see in the night sky is a lie. Not a deception of intent, but a fundamental illusion woven into the very fabric of space and time. The light from those distant suns has traveled for years, for centuries, sometimes for millennia to reach your eyes. You are not seeing stars as they are now. You are seeing ghosts, echoes of a fire long past. This delay, this cosmic latency, is the first and most profound clue to our predicament, our cosmic isolation. It is the gentle whisper of the first reason why we may never leave our home galaxy, the sheer soul-crushing distances. We call our galaxy the Milky Way. It feels like a grand name for a grand place, our home. But a home can also be a prison. This island of 200 billion stars, a swirling disk of light, 100,000 light-years across, is our entire world. And to leave it to even contemplate the journey, we must first come to terms with its impossible scale. We have invented a unit of measure to try and comprehend it, the light year. The distance, a beam of light, the fastest thing in the universe, travels in a single terrestrial year. It sounds so simple, so elegant, but the number it represents is a monster. Nearly 6 trillion miles, almost 10 trillion kilometers. A number so large it loses all meaning. Let us try to give it shape. Our fastest space probe, the Parker Solar Probe, can reach speeds of over 400,000 miles per hour, a breathtaking velocity born of immense gravitational assists. At that speed, a speed that would circumnavigate the Earth in less than 4 minutes, it would still take that probe over 1,500 years to travel a single light year. 15 centuries locked in the cold, silent dark, just to cover the most basic unit of galactic distance. And where would that journey take us? To our nearest stellar neighbor, Proxima Centauri, a small, dim red dwarf star, part of the Alpha Centauri system. It is practically on our celestial doorstep, the closest sun to our own. It is 4.2 light-years away. 4.2 times 1,500 years. Our fastest machine would need more than 6,300 years to complete the journey. 6 millennia. Humanity began writing its first words around that long ago. The Great Pyramids of Giza had not yet been conceived. Civilizations would rise, flourish, and crumble to dust in the time it would take one of our probes to greet the next star. The crew, their children, their grandchildren, their entire lineage for 200 generations would be born, live and die in the void between suns. A ghost ship of human ambition, its original purpose lost to the mists of its own impossibly long history. This is not a technological problem waiting for a solution. It is a fundamental boundary imposed by the cosmos. We think of space as empty, but that emptiness itself is the obstacle. It is a gulf of such profound magnitude that it mocks our most ambitious engineering and our very biology. Our lifespans are a flicker against this monolithic timescale. Our history is a footnote, and that is just the first step, the very first tentative step off our cosmic front porch. Imagine we wish to be more adventurous. Let us aim for Sirius, the brightest star in our night sky. A brilliant blue-white jewel twice the size of our Sunday. It resides 8.6 light-years away. The journey is now 13,000 years. Humanity was just emerging from the last ice age 13 millennia ago, painting stories on cave walls. Let us be bolder still. Let us travel towards the heart of our galaxy, to the magnificent, terrifying supermassive black hole, Sagittarius A, that binds our stellar family together. It is a journey of 26,000 light-years. At the speed of our fastest probe, that voyage would last not for millennia, but for 39 million years. 39 million years ago, the ancestors of humanity were small primates just beginning their evolutionary journey. The continents themselves were in a different configuration. Mountains would be born and erode into sand during the transit time. The very species that launched the vessel would likely be extinct, transformed by evolution into something entirely unrecognizable. The ship would arrive at a destination of unimaginable wonder, a relic from a vanished world its creators long since turned to fossils. The scale of the Milky Way is not merely a geographic challenge, it is a temporal abyss. Each light year is a barrier woven from time itself. The galaxy does not forbid us from leaving, it simply presents a tapestry of such immense size that to cross it is to leave behind everything we are. It demands a price in time that no single generation, no single civilization, perhaps no single species can ever pay. This is the first reason, the great wall of distance that may forever confine us to our tiny corner of the cosmos. The very grandeur we admire is the architecture of our cage. But let us for a moment entertain the fantasy. What if we could build something faster, something that could conquer these distances, that could shrink the millennia into mere decades? This is where hope often resides, in the dream of velocity. But as we chase this dream, as we reach for the stars, we slam headfirst into the second, more brutal reason we may never escape our galactic home: the staggering, inconceivable requirements of energy. To move through space is to wage war against a fundamental property of the universe: inertia, the resistance of any physical object to a change in its state of motion. To start moving, to accelerate, you must expend energy. To accelerate something massive like a starship capable of sustaining human life to a meaningful fraction of the speed of light, the energy required is not just large, it is planetary, it is solar, it is beyond comprehension. This isn't a matter of building a better engine. It is a confrontation with the most basic laws of physics encapsulated in a single merciless piece of mathematics: the tyranny of the Tsiolkovsky rocket equation. Konstantin Tsiolkovsky, a pioneering Russian scientist, laid down the fundamental principle of rocketry over a century ago. His equation is elegant, beautiful, and utterly cruel. It states that a vehicle's change in velocity depends on the velocity of its exhaust and the ratio of its initial mass with all its fuel to its final mass after that fuel is burned. The implication is a nightmare of diminishing returns. To go faster, you need more fuel, but that fuel has mass, so now you need even more fuel just to accelerate the first batch of fuel, which in turn adds even more mass, which demands yet more fuel to push it all. It is a vicious compounding cycle. A cosmic tax with an exponential rate. Imagine packing for a very long hike. You need food, so you put it in a backpack. The food is heavy, so you need more energy and thus more food to carry it. This extra food adds more weight, requiring even more food to compensate. Very quickly, your backpack becomes impossibly large, filled almost entirely with the food needed just to carry the other food. Your actual supplies, your destination gear, become a tiny, insignificant fraction of the total weight. Now scale that problem up to interstellar travel. The backpack is your starship, the food is your fuel, and the journey is not for a few days but for light years. Let's use the most efficient chemical propellants we can imagine, the kind that power our rockets to orbit today. If we wanted to accelerate a modest spacecraft, say the size of a bus, to just 10% of the speed of light for a trip to Proxima Centauri, the amount of fuel required by the rocket equation would be a sphere larger than our entire solar system. The mass of the fuel would exceed the mass of all the planets, moons, and the sun itself combined. It is a physical absurdity, a mathematical dead end. Chemical rockets, the very tools that opened the space age, are the cosmic equivalent of trying to cross the Pacific Ocean in a rowboat. They are fundamentally, hopelessly inadequate for the task, so we must look beyond. We must imagine more powerful, more exotic forms of propulsion, perhaps nuclear power. Project Orion, a concept born in the Cold War, envisioned a colossal ship propelled by a series of atomic explosions, detonating nuclear bombs behind the vessel, blasting it forward on waves of pure raw power. It is a magnificent, terrifying, and brutal idea, and while far more efficient than chemical rockets, it still bows before the tyrant Tsiolkovsky. The ship would need to carry tens of thousands, perhaps hundreds of thousands of nuclear devices. The vessel would be less of a starship and more of a moving thermonuclear arsenal. The sheer mass of the bombs themselves, the shielding required, the gargantuan pusher plate needed to absorb the blasts, all add to the initial mass, and the equation's cruel calculus kicks in once more. The hike is still too long, and the backpack is still too heavy. Fusion rockets, which would harness the power of a miniature sun, offer even greater efficiency. They would fuse light elements, like hydrogen, into helium, releasing tremendous energy and high-velocity exhaust. This is a far more elegant solution, the kind of engine that fuels science fiction, yet the physics remains stubborn. The fuel isotopes of hydrogen, like deuterium and tritium, still has mass. The powerful magnetic fields needed to contain a star in a bottle require colossal, heavy superconducting magnets. The power plants, the radiators to shed waste heat, the life support, it all adds up. Mass, and more mass. Even with fusion reaching a significant percentage of light speed requires a fuel-to-payload ratio that is staggering. For every ton of ship that reaches the destination, thousands of tons of fuel must be consumed. We are making the rowboat bigger, giving it a motor, but the ocean remains just as vast. This leads us to the theoretical pinnacle of propulsion, the most potent fuel source permitted by the laws of physics, antimatter. When a particle of matter meets its antimatter counterpart, they annihilate one another completely. Their entire mass is converted into pure energy with 100% efficiency, according to Einstein's famous equation E = mc². This is the holy grail of energy production, An antimatter engine would be thousands of times more powerful than even a fusion drive. Surely this is the key, the way to defeat the rocket equation. But the universe rarely offers a solution without a profound catch, and the catch with antimatter is threefold. First, creating it. Antimatter does not exist in nature in any usable quantity. We must forge it particle by particle in immense accelerators. The energy cost is astronomical. To create a single gram of antimatter with our current technology, we would need to expend more energy than all of humanity consumes in an entire year. To produce the tons required for an interstellar mission would require the energy output of hundreds of stars. We would need to build a civilization-spanning industrial complex of unimaginable scale just to fuel a single voyage. Second, storing it. How do you hold something that annihilates anything it touches? You must suspend it in a perfect vacuum using powerful magnetic fields. The containment system would have to be flawless, operating without interruption for decades or centuries. A single power failure, a single stray atom wandering into the trap, and the result would be an explosion of such violence it would make a hydrogen bomb look like a firecracker. Our starship would not just be a vehicle, it would be the most unstable and dangerous object ever created. A city killer bomb we are trying to ride to the stars. And third, even with this perfect magical fuel, the ghost of Tsiolkovsky still haunts us. The efficiency is vastly improved but not infinite. You still need to carry your antimatter fuel and your regular matter to react it with. That fuel has mass, the containment system has mass, the magnetic bottle is heavy. To reach speeds approaching that of light, say 90%, the mass ratios are still punishing. The problem is mitigated, but it is not solved. The equation, the iron law of motion, will not be broken. It tells us that to move through space carrying your own fuel is a fundamentally inefficient and costly endeavor. It's as if the universe itself is telling us if you want to travel between the stars, you cannot take the journey with you. This leads us to the raw energy cost itself, a separate problem from the tyranny of mass ratios. Let's pretend we have a magic engine, a device that requires no fuel that somehow violates the rocket equation. Even with this impossible machine, we face a wall of pure energy. The kinetic energy of an object, its energy of motion, increases with the square of its velocity. Doubling your speed doesn't double the energy cost, it quadruples it. This scaling law is just as unforgiving as Tsiolkovsky's equation. Let us imagine a substantial starship. Not a small probe, but a true ark capable of carrying a human crew and its support ecosystem. Let's give it the mass of a modern aircraft carrier, about 100,000 tons. A tiny speck compared to a planet, but a significant feat of engineering. Now let's accelerate this arc to 50% of the speed of light, half c, a velocity that would make the journey to Proxima Centauri take a little under a decade, a genuinely viable timescale. What is the energy bill for this acceleration? The kinetic energy required would be approximately 1.3 times 10 to the 24th joules. That is a number so vast it is functionally meaningless. Let's anchor it to reality. That amount of energy is more than the entire human species, with all its power plants, all its industry, all its consumption, has generated in its entire recorded history. Multiplied by 1,000, it is equivalent to the total energy the sun radiates into space over the course of several minutes. The sun, a thermonuclear furnace 1,000,000 times the size of Earth. We would need to capture and perfectly channel the complete output of our parent star for a considerable time just to provide the initial push for a single starship. Where could such power possibly come from? The most ambitious theoretical megastructures, like a Dyson sphere, which would encase an entire star to harvest all its energy, are conceived for powering an entire interstellar civilization. Here we find that the total output of such a structure would be required simply to launch one ship on one journey. It is a cosmic bank account with insufficient funds. The startup cost for interstellar travel is the treasury of a star. And that's only half the story. Once you arrive at your destination, you are still traveling at 50% of the speed of light. You have to slow down. To decelerate, you must expend the exact same amount of energy all over again, so you must double the price. Our energy bill is now 2,000 years of total human civilization's output, or the full power of a captured star for several minutes spent twice. This is the second reason, the Great Barrier of Energy. It stands behind the wall of distance, reinforcing it. The two problems are locked in a deadly embrace. The immense distances demand immense speeds. Those immense speeds demand impossible, civilization-breaking amounts of energy governed by physical laws that punish ambition with exponential costs. It's a cosmic catch-22. To conquer the distance, you must generate the energy of a sun. But to do so requires a level of mastery over the cosmos that suggests you should already be a star-faring species. We are left staring across an ocean of space-time, knowing the precise distance to the other shore. We can see the light from it, a faint glimmer of promise. But we are standing here with a thimble tasked with emptying a sea of its water to build a bridge. The tools of physics as we understand them, the very rules of energy and motion that govern our universe, do not seem to be on our side. They have built us a magnificent home in this galaxy, but they have also bolted the doors with the mathematics of infinity and hidden the key in the heart of a star. Imagine a promise whispered from the laws of physics themselves, a way to cheat the tyranny of the clock to outrun decay. It is perhaps the most profound, most seductive consequence of our understanding of the universe, a gift from Einstein. The faster you move through space, the slower you move through time. This is the third barrier, a paradox disguised as a miracle. It is the chilling realization that to travel between the stars is to embark on the loneliest voyage imaginable, a journey not just across space but through the heart of time itself. Let us say we build it our magnificent interstellar ark, a vessel capable of approaching a significant fraction of light speed. You board this ship, a pioneer for all humanity. You say your goodbyes to loved ones, to your entire world, promising to return with tales of alien suns and new worlds. The engines ignite a torrent of controlled fury, and as your velocity climbs, something extraordinary begins to happen. To you aboard the ship, everything feels perfectly normal. Your watch ticks once per second. Your heart beats at its usual rhythm. But from the perspective of Earth, your clock has begun to lag. Your journey to a nearby star system, say 20 light-years away, might take you, the traveler, only a few years of subjective time. You are granted a longer life to complete your mission. This is the gift of time dilation. But the universe is a scrupulous accountant. Nothing is given for free. For every second of time you saved for yourself, decades have mercilessly scythed by on the world you left behind. The price of your journey is the future of your species. When you decide to return, you are not coming home. You are traveling to a world that has forgotten you. The family you left, your friends, your colleagues, they are all gone. They are dust footnotes in digital histories you no longer recognize. The child you left behind might be a grandparent or more likely a name on an ancestral chart. The cities you knew have transformed into archaeological layers. Languages have shifted, cultures have mutated into unrecognizable forms. Every landmark, every institution, every cherished memory has been eroded by the relentless current of the years you skipped. You would be an artifact, a living fossil from a forgotten epoch, a stranger on your own planet, haunted by the ghosts of an entire world. This is not a technological problem to be solved with a clever engine. It is a fundamental consequence of reality woven into space-time. It is an insurmountable wall of human feeling of connection and loss. What is the purpose of exploration? if it requires a total sacrifice of everything that makes the explorer human, who would sign up for this temporal exile to become a lonely god, adrift in the ocean of millennia, forever disconnected from the warm shores of a shared present? The psychological burden would be catastrophic, a crushing solitude that no amount of training could ever prepare a mind to endure. So we envision a different kind of solution, a tragic monument to our ambition born from this impossible dilemma. If no single lifetime can bridge the gulf, then perhaps many can. We conceive of the generational ship, a vessel so vast it is not merely a transport but a world unto itself. An ark carrying a microcosm of humanity, a seed of civilization launched into the cosmic dark with no expectation of return for its crew. Its mission is not for those who depart, but for their descendants. Generations would be born, live their entire lives, and die within the cold metal confines of this manufactured star. Their only sky, a simulation, their only ground, a spinning drum. Think of the sheer audacity, the profound melancholy of such an undertaking. The first generation are the pioneers, the visionaries. They carry the fire of purpose, the memory of green hills and blue skies. They know what they are sacrificing and why. But what of the second generation, or the fifth, or the 20th? They are born into a prison they did not choose, a hermetically sealed society drifting through an endless night. Their lives are dedicated to a destination they will never see. They are merely a link in a biological and cultural chain, a bridge of bone and dream stretching across the void. What kind of society could survive such a journey, trapped for centuries, 1,000 years, perhaps more? The psychological pressures would be immense. Claustrophobia, social stagnation, the loss of purpose. How do you maintain the intricate technical knowledge to operate a starship across 30 generations of farmers and poets? How do you prevent the rise of dogma, of new religions that might declare the journey heretical, the destination a myth? The ship itself, a marvel of engineering, would be a fragile ecosystem. A single catastrophic failure in life support, a genetic bottleneck, a plague, a civil war, any could doom the entire enterprise. The original crew makes the ultimate sacrifice. They trade their lives and the lives of all their progeny for a dream that will only be realized by a people so distant in time they would be like a foreign species. A people who might not even remember the name of the planet from which their ancestors so bravely, so foolishly departed. The generational ship is not a vessel of hope. It is a tomb in motion, a monument to a species so desperate to escape its cradle that it would sacrifice its own children to the void. It is an answer to the problem of time that creates a dozen more unanswerable questions about what it means to be human. But let us imagine we solve even this. Imagine we discover a way to endure the psychological abyss, to build a society that could withstand a 1,000-year voyage. Even if we could conquer the tyranny of time and the fragility of the soul, the universe presents a fourth, more immediate and more violent barrier. The cosmos is not empty. That serene, silent blackness you see between the stars is a lie. Interstellar space is a shooting gallery, a lethal wilderness. And on a journey to another star, our ship would not be a vessel, it would be a target. The first peril is invisible, insidious, and inescapable. It is a constant, unending storm of lethal radiation. We call them galactic cosmic rays, but that gentle name betrays their true nature. They are not rays of light, they are fragments of atoms. The nuclei of hydrogen, helium, all the way up to iron, forged in the hearts of ancient supernovae in the churning maelstroms of black holes and neutron stars across the galaxy. These particles have been accelerated over millions of years to velocities approaching the speed of light. They are subatomic shrapnel tearing through the cosmos. Here on Earth we are profoundly lucky. We live at the bottom of a deep protective well. Our planet's molten iron core generates a powerful magnetic field, a vast invisible shield that deflects the worst of this onslaught. What breaks through is then absorbed by our thick atmosphere. We are sheltered, but in the interstellar void, there is no shelter. A starship would be naked, exposed to the full raw fury of the galaxy. These high-energy particles would pass through a metal hull as if it were tissue paper. They would slam into the bodies of the crew, a relentless bombardment. Each impact is a microscopic catastrophe. A single iron nucleus, traveling at near light speed, carries the kinetic energy of a thrown baseball. It smashes through cells, shattering the delicate helix of DNA. It creates a shower of secondary particles, a cascade of destruction that multiplies the damage as it travels through tissue. The effects are devastating and cumulative. Over time, this constant assault would lead to rampant cancers. It would cause cataracts, damage to the central nervous system, and induce rapid premature aging. It could degrade cognitive function, erasing memories, erasing minds. And this is just the background hum of the cosmos. The galaxy is also prone to sudden violent outbursts. A nearby star could unleash a colossal flare, a stellar tantrum blasting out a wave of radiation orders of magnitude more intense. Such an event could deliver a fatal dose to an unshielded crew in hours. Our ship would have to be a fortress, a radiation vault. But how do you build such a thing? Shielding requires mass, thick layers of lead or vast tanks of water. But every kilogram of shielding is another kilogram the engines must push. This is the brutal tyranny of the rocket equation. More mass requires exponentially more fuel. More fuel means a larger, heavier ship, which in turn needs more shielding. The numbers spiral out of control into impossibility. We could devise powerful magnetic fields to deflect charged particles, but this would require a titanic power source, a reactor of unimaginable output itself, a source of radiation demanding its own shielding. And even a magnetic shield is useless against uncharged radiation like gamma rays, or against another more tangible threat. The problem of the universe hitting back, for the interstellar medium, is not just a storm of particles, it is also seeded with dust and debris. On Earth, a grain of sand is harmless, a tiny pebble is a trifle. But in the context of interstellar travel, they are weapons of mass destruction. The danger is not in their size, but in their velocity. Kinetic energy increases with the square of speed. When you are moving at 10, 20, 50% of the speed of light, the reference frame is inverted. It is not you hitting the dust grain. It is the dust grain hitting you with incomprehensible force. A microscopic speck of dust, barely visible to the naked eye, would impact your ship with the explosive energy of a hand grenade. A particle the size of a grain of sand would strike with the force of a tactical nuclear weapon. It would not simply puncture the hull. It would vaporize a portion of it, creating a rapidly expanding cloud of superheated plasma that would obliterate everything in its path. The ship would be sandblasted into oblivion over time, pummeled by a relentless barrage of microscopic bombs. A single pebble the size of a small coin would be a cataclysm. It would spell the instantaneous explosive end of the entire mission, a silent flash of light in the unending darkness. How do you shield against this? How do you build a barrier that can withstand an impact, delivering the energy of tons of TNT every few days or weeks? A physical shield, a massive plate of armor at the front of the ship, would itself be eroded, ablated away by the constant impacts. It would have to be impossibly thick, impossibly heavy, throwing us back into the merciless arms of the rocket equation. Perhaps a Whipple shield, a series of thin, spaced-out layers designed to break up and vaporize an incoming projectile. But this offers no protection against the constant slow death of radiation or the sheer number of microscopic impacts. Scientists have proposed exotic solutions, a cloud of plasma held in front of the ship by magnetic fields. a powerful laser system to detect and vaporize threats from afar. But the energy requirements are astronomical. The precision needed is staggering. You would have to detect a grain of sand from millions of kilometers away, then target and destroy it in a fraction of a second. This defensive system would have to operate flawlessly without a single error for the entire duration of a journey lasting centuries. One failure, one miscalculation, one pebble that slips through the net, and the entire multi-generational effort is rendered into atoms. So we find ourselves trapped in a cosmic checkmate. The dilemma of time forces us to travel faster, to cross the interstellar gulf within a manageable human timescale. But the faster we travel, the more violent and certain our destruction becomes. The energy of each impact, the lethality of the void rises exponentially. To slow down is to surrender to the despair of generational ships, to the crushing psychological toll and the slow death by radiation. To speed up is to fly headlong into a wall of pure energy, to face a barrage of cosmic bullets from which there is no escape. The very laws of physics that allow for the journey seem to have conspired to make it impossible. The universe, it seems, guards its treasures jealously, and the price of admission to another star system may be a cost no civilization can ever afford to pay. Of all the barriers that stand between humanity and the stars, none seem more temporary, more transient than technology. We are toolmakers after all. What we cannot do today, we will surely achieve tomorrow. Our ascent from sharpened stone to interplanetary rover seems to prove that no challenge is ultimately beyond our grasp. We look at the void and see not an impassable gulf, but merely an engineering problem awaiting a solution. This optimism is our species' greatest strength. It may also be our most profound delusion, because when we confront the physics of interstellar propulsion, we are not wrestling with a simple lack of cleverness. We are running headfirst into the universe's most fundamental laws. The problem is not that our engines are too weak. The problem is that the universe demands a price for speed, a price so fantastically high it borders on the impossible. To understand this cosmic toll, we must first face a tyrant, a simple, elegant, and utterly merciless piece of mathematics known as the Tsiolkovsky rocket equation. It is the monster that haunts the dreams of every astronautical engineer. In its cold logic, there is no sentiment, no room for hope. It governs how much you must throw out the back of a ship to change its forward velocity. It tells a brutal story of diminishing returns. To go a little faster, you need more fuel. But that fuel has mass, which makes your ship heavier. So to push that heavier ship, you now need even more fuel, which of course adds even more mass. This feedback loop, this compounding crisis of weight, is why our mighty Saturn V rockets' titans of chemical power were almost entirely fuel tank. Over 95% of their colossal mass was propellant, all expended just to place a tiny capsule into Earth orbit and then nudge it gently towards our own moon. It was a supreme achievement, but on a cosmic scale, it was the equivalent of taking a single step off our front porch. To reach another star using that same chemical technology is not just difficult, it is a mathematical absurdity. The amount of fuel required would exceed the mass of our sun. The rocket itself would need to be larger than our solar system. The equation doesn't just say no, it screams it. So we discard the fire of chemical combustion. We must turn to a deeper source of power. We must look to the very heart of the stars themselves. This brings us to the great hope of realistic interstellar travel, the fusion drive. It is the dream of bottling a miniature sun, of capturing the raging heart of a star in a magnetic field and channeling its thermonuclear fire into a directed jet of plasma. The energy release is titanic, millions of times greater than any chemical reaction. The exhaust can be expelled at a significant fraction of light speed. This is the technology that powers the starships of our dreams, the engine that seems to promise a path to the galaxy. Let us imagine for a moment that we have solved it. that after centuries of toil we have mastered this stellar alchemy. We can build a fusion engine. The first obstacle we face is not the engineering but the fuel. The most efficient fusion reactions require rare isotopes. Things like deuterium, which we can filter from our oceans, but also tritium, a radioactive substance that decays in years. Or better yet, helium-3, an isotope vanishingly rare on Earth. To fuel even a single interstellar voyage, the quantities required are staggering. Where do we find such a cosmic treasure? The answer is written in the clouds of giants. The atmospheres of Jupiter and Saturn are rich in helium-3 deposited there by billions of years of solar wind. So the prerequisite for building our first starship is to first construct a colossal industrial infrastructure thousands of times more advanced than anything we have today. We would need fleets of autonomous atmospheric miners scooping fuel from the crushing pressures of Jupiter's storms. We would need refineries in orbit, separating isotopes at scale. We would need a supply chain that spans the entire solar system. We would have to become a true interplanetary species, masters of our own cosmic backyard, simply to gather the resources to fill the fuel tank for one mission. This is the endeavor of a civilization, not a single nation, an effort sustained over centuries just for the initial buy-in. Now let us consider the engine itself. This is no simple machine. It is a star, constrained. It requires magnetic fields of unimaginable power to contain plasma heated to hundreds of millions of degrees, a temperature far hotter than the core of our own sun. A momentary flicker in that containment, a single instability, and the ship would be instantly vaporized by its own power source. The engine would be bombarded by a storm of high-energy neutrons requiring thousands of tons of radiation shielding just to protect the crew and the ship's own electronics. The vessel built around this engine would not be sleek or elegant. It would be a gargantuan structure kilometers long, a fragile human habitat bolted to a barely tamed artificial star, its mass dominated by fuel shielding and cooling systems. And after all this, after centuries of preparation, after mastering our solar system to fuel and build this behemoth, what have we bought ourselves? With a continuous fusion drive pushing relentlessly for years, we might, if we are incredibly optimistic, achieve 10, perhaps 15% of the speed of light. A blistering 30,000 kilometers per second. At that velocity, the journey to our nearest neighbor, Proxima Centauri, a paltry 4 light-years away, would still take 3 decades. A mission to a more promising star system, perhaps 120 or 30 light-years distant, becomes a multi-century odyssey. The crew who leaves Earth will never see their destination. Their children might, or their children's children. This is not exploration as we know it. It is a form of generational exile. A decision by one generation to condemn their descendants to a life lived and died in a metal, can hurtling through an eternal night, all for the hope of reaching a world they have never known. The fusion drive, our most realistic and powerful future technology, turns the journey to the stars into a profound moral question. It reveals that even with the power of a sun at our command, the galaxy does not simply yield. It demands a price in human lifetimes. But perhaps there is another way, a source of power so absolute it seems, to cheat the equations, the ultimate energy source permitted by the laws of physics, antimatter. It is the universe's mirror image. For every particle there is an antiparticle. When they meet, they do not collide, they annihilate. Their entire mass is converted into pure energy, a flash of gamma rays with 100% efficiency. This is the promise of Einstein's most famous equation, E equals mc squared, made real. The energy locked within a single gram of antimatter is equivalent to a strategic nuclear weapon. A few dozen kilograms could, in theory, accelerate a starship to over 90% of the speed of light. Journeys that took centuries with fusion could be completed in years. relativistic time dilation would mean that for the crew, the voyage to a nearby star might feel like mere months. This is it, the key that unlocks the galaxy. Except antimatter presents us with a series of paradoxes, each more daunting than the last. The first is its very existence. In our universe, matter won. After the Big Bang, for every billion particles of antimatter, there were 1,000,000,001 particles of matter. That tiny asymmetry is the reason we exist. It is why the cosmos is filled with galaxies, stars, and planets, instead of being a featureless bath of pure energy. Antimatter does not exist in nature, not in any usable quantity. It must be created, and the only way we know how is in colossal particle accelerators smashing protons together with titanic force. The process is monumentally inefficient. To create a single gram of antiprotons with our current technology would require all of the power plants on Earth running continuously for several 100,000 years. The energy you must invest to create the fuel is orders of magnitude greater than the energy you get back out. It is the most expensive, most energy-intensive substance that is physically possible to make. Building the infrastructure to produce kilograms of it would require harnessing the entire energy output of our sun. We would need to build a Dyson swarm or something equivalent, a civilization-scale megastructure just to power the antimatter factory for a single starship. But let us imagine again that we have done it, that a future super-civilization has accomplished this feat. Now we have a new problem, perhaps the most terrifying of all storage. How do you hold something that annihilates on contact with anything? You cannot put it in a bottle. The bottle is made of matter. The only solution is to hold it in a perfect vacuum levitated by powerful magnetic and electric fields, a device called a penning trap. This containment field must be flawless, and it must be powered continuously without interruption for the entire duration of the journey. A momentary power surge, a system malfunction, a stray micrometeoroid that disrupts the fields for even a nanosecond, and the fuel touches the wall of its container. The resulting annihilation would not be an explosion, it would be an erasure. The ship, the crew, everything for kilometers around would vanish in a silent, lethal flash of gamma radiation, brighter than 1,000 suns. Your fuel tank is the most powerful bomb it is possible to construct. Your voyage to the stars is perpetually a heartbeat away from utter and complete annihilation. And even if you can produce it, even if you can store it, you must still build an engine around it. An engine that can somehow take this perfectly controlled annihilation and channel its terrifying energy into a coherent, propulsive jet. This is a challenge of materials, science, and physics that makes a fusion reactor look like a simple steam engine. How do you build a magnetic nozzle that can direct gamma rays? How do you manage the colossal waste heat from the reaction without melting the entire engine assembly into slag? Antimatter propulsion is the ultimate paradox. It is the only known fuel that makes interstellar travel feasible in a human lifetime, but its production and containment are so monumentally difficult, so profoundly dangerous, that a civilization capable of mastering it would already need to be a godlike master of energy and matter. It's like needing to build a skyscraper to get the bricks to build the foundation of a small house. The solution demands a capability far beyond the problem it sets out to solve. And here we arrive at the precipice. We have looked at the very best our physics can offer. We have imagined harnessing the power of stars and the fury of annihilation. And in every case, we have found the price to be crushingly, perhaps prohibitively high. The sheer quantity of energy and resources required to move a physical object through the vast emptiness of space-time is a barrier that seems to grow higher the more we study it. The universe, it seems, does not want us to travel between the stars. This realization forces a profound shift in our thinking. It leads us to a stunning, almost mystical conclusion. Maybe the problem isn't our engines. Maybe the problem is the very idea of moving through space. What if instead we could move space itself? This is where science ends and speculation begins. This is the realm of technologies that exist only as equations on a blackboard, tantalizing whispers of a physics we do not yet grasp. The first and most famous is the warp drive. Popularized in fiction, its scientific basis is a concept developed by physicist Miguel Alcubierre. It proposes a way to travel faster than light without ever breaking the light speed limit locally. It is an act of supreme cosmic cheating. The idea is to create a bubble of flat, normal space-time around the ship. The ship itself would be at rest inside this bubble, experiencing no acceleration. Then you would use an engine to warp the fabric of space-time itself, violently contracting the space in front of the bubble and dramatically expanding the space behind it. The bubble with the ship inside is carried along on this wave of space-time, like a surfer on a tidal wave. Because it is space itself that is moving, not the ship, the theory of relativity is not violated within the bubble. You could cross the galaxy in a matter of weeks. It is the perfect solution. And it is almost certainly impossible. The Alcubierre metric, the mathematical blueprint for a warp drive, requires the existence of something called exotic matter. This is not just matter that is strange or rare. It is a substance that must have negative mass or negative energy density. Think of it as matter with anti-gravity. It would fall up, not down. It would push rather than pull. We have searched for such a substance. We have never found it. Our current understanding of physics suggests it cannot exist. It seems to be forbidden by the fundamental laws of reality. Even if it did exist, the energy requirements are breathtaking. Early calculations suggested you would need a ball of exotic matter with the mass of the entire observable universe. More recent optimistic models have reduced that requirement to something on the order of the mass of the planet Jupiter. So, to start your warp drive, you must first find a way to convert a gas giant into a substance that probably doesn't exist. Furthermore, the theory predicts other, more lethal side effects. The front of the warp bubble would act as a cosmic snowplow, accumulating interstellar particles and radiation into a deadly beam. Upon arrival at your destination, when you turn the drive off, this beam would be released, annihilating everything in your path with the energy of a supernova. You would be the ultimate harbinger of death, an unwitting destroyer of worlds. The warp drive is a beautiful mathematical idea, a testament to the power of human imagination to bend the rules. But it appears to be a door that the universe has firmly locked and bolted. So we turn to the final, most ancient dream of a shortcut. Not to travel faster than space, but to travel outside of it. The wormhole. Known technically as an Einstein-Rosen bridge, it is a theoretical tunnel through space-time. A tear in the cosmic fabric that connects two distant points like a secret passage between two rooms in a colossal mansion. You could step through a gateway in our solar system and emerge moments later in the Andromeda galaxy 2.5 million light-years away. The concept emerges directly from Einstein's theory of general relativity. It suggests that space-time can be curved, bent, and perhaps even torn. Wormholes might be a natural, if rare, feature of the cosmos, but once again the universe gives with one hand and takes away with the other. The theoretical wormholes predicted by relativity are unstable. The instant they form, they would snap shut with such violence that not even a single photon of light could pass through. They are transient, fleeting, and utterly impassable. To hold one open to stabilize it long enough for a ship to travel through requires once again that same magical ingredient, a vast quantity of exotic matter with negative energy. You would need to somehow find this impossible substance and use it to prop open the throat of the tunnel, fighting against the natural tendency of space-time to heal itself. And we have no idea how one would be created, or how you would find its other end, or how you would survive the tidal forces and lethal radiation believed to exist at its core. Like the warp drive, the wormhole appears to be a cosmic tease, a mathematical possibility that is likely a physical impossibility. And this is the final sobering revelation. This is the fifth barrier. Our known propulsion technologies are defeated by scale. Our best theoretical engines are defeated by resource requirements that demand a godlike command of planetary engineering. And our only speculative hopes for a true shortcut are defeated by the apparent laws of physics themselves. They require us to find a form of matter that our universe has chosen not to create. The great silence in the night sky may not be because we are alone, it may be because the universe is a collection of islands, countless solar systems, each a cradle of possibility but separated by a gulf of space-time so vast and so unforgiving that it acts as the wall of a cage. The speed of light is not just a cosmic speed limit, it is the ultimate prison bar. It enforces a fundamental isolation. Without a revolution in physics, a discovery so profound that it overturns everything we think we know, we may be forever bound to our stellar nursery. This is not a failure of will or a lack of imagination. It may be a fundamental truth of our existence. We are creatures of a single star, and the silent, glittering promise of the Milky Way may be a beauty we are destined to admire, but never ever to touch. Let us imagine the impossible has been achieved. The engine that folds space, the shield that parts the interstellar medium, the power source that can burn for 100,000 years. Let us presume we have conquered the physics of the void. The greatest journey in human history is finally ready to begin. But in solving for the cosmos, we have overlooked the final and most turbulent variable in the entire cosmic equation: ourselves. The true void is not the vacuum waiting outside the hull. It is the expanding emptiness between one human mind and the next, stretched across an unimaginable expanse of time. The most profound barrier to the stars may not be a law of physics. It may be the fundamental, unchangeable, and fragile architecture of the human soul. Consider the first generation, the pioneers. They are heroes, visionaries, the bravest among us. They will step aboard this magnificent vessel, a self-contained world, and they will say their final farewells to everything. To blue skies and open oceans, to the scent of rain on dry earth, to the comforting gravity of a home they will never feel again. Their mission is a sacred trust, a promise made to the future. But it is a promise they will never see fulfilled. They are the bridge, the vital, sacrificial link. They will live and work and love and grow old and die in transit, their entire existence, a prelude to someone else's arrival. What does this knowledge do to the human spirit? To know that your entire life is an epilogue to one world and a prologue to another, but never a complete story in itself. Psychologists call the potential condition generational melancholia, a profound sense of purposelessness, born from a deferred destiny. The pioneers are living ghosts haunted by a future they cannot reach, and a past that is receding from them at nearly the speed of light. Every star they pass is a reminder of their impossible distance. Every transmission from a fading Earth, delayed by decades, becomes a voice from the grave, a historical artifact. They are the sole caretakers of humanity's most precious cargo, the dream of a new beginning. But who takes care of the caretakers? The starship itself, this marvel of engineering, becomes a paradox. It is both a sanctuary and an inescapable eternal prison. It is a perfect closed ecosystem, a technological womb. The air is scrubbed and recycled, the water purified and returned. The light is a perfect simulation of a sun that is now just a memory. The horizons do not expand, they are fixed, metallic, unyielding. For the first generation, these are acceptable sacrifices. But what about the 5th, the 10th, the 50th? To them, Earth is not a memory, it is a myth. a collection of ancient stories of two-dimensional images of words spoken by long-dead ancestors about a place called ocean or a feeling known as wind. How can you long for something you have never known? The very concept of outside begins to dissolve. The ship is their universe, the only one they will ever know. This is the genesis of the generation ship psychosis, a theoretical condition where the inhabitants of the microcosm can no longer conceptually grasp the macrocosm. The idea of a planet, a vast open sphere of rock and water, becomes as alien and terrifying as a creature from deep space. They live within a machine that provides for their every need, a benevolent, all-encompassing god of metal and plasma. The ship's maintenance schedules become a religious calendar. The engineering deck becomes a holy sanctum. The captain's logs transform into scripture. The original mission statement, preserved over centuries, could warp into a creation story, its meaning lost to dogma. And what of society itself? This fragile ecosystem of souls, on Earth civilizations, have space to breathe, to expand, to fail. Cultures can clash, merge, or retreat from one another. There is always somewhere else to go, a new frontier to cross. But on a starship, there is no frontier. There is no somewhere else. Every social friction, every ideological disagreement, every personal grudge is amplified in the confines of the vessel. It is an echo chamber of humanity where resentments can fester and ripple through generations, becoming blood feuds whose origins are lost to the mists of ship time. How do you govern such a place for 10,000 years? A democracy, its short-term cycles might be too unstable for a mission requiring millennia of unwavering focus. A technocracy run by engineers, it could breed a rigid caste system pitting the knowers of the machine against the passengers. A military command aboard a ship with no external enemies, the military might eventually turn its focus inward on the populace. Perhaps the answer is an artificial intelligence, a benevolent, logical overseer immune to human emotion and corruption. An AI could manage resources, mediate disputes, and hold the mission true. But what happens when the 100th generation begins to see this AI not as a tool but as a tyrant, a cold, unfeeling god dictating their lives from a throne of logic and code? A rebellion against an AI is not just a mutiny, it is a war against the very life support system of their universe. The social fabric is stretched thin by another, more insidious force, the simple, brutal reality of mathematics, the unforgiving mathematics of the gene pool. To found a viable new human colony, you need genetic diversity. Thousands of unrelated individuals are required to avoid the bottleneck of inbreeding and the resultant catastrophic health defects. Our starship must therefore carry a population of 10, 20, perhaps 50,000 souls to remain genetically stable. But even this presents a chilling ethical dilemma. For millennia, partnerships cannot be left to chance, to love, to fate. Every birth must be a calculated decision, a strategic move in a long and desperate game against genetic decay. Who makes these decisions? A breeding committee, an algorithm. Imagine being told that your life partner will be chosen for you based not on compatibility or affection, but on genomic sequencing. Imagine that the person you truly love is genetically forbidden. This is a recipe for despair, for black markets of affection, for secret alliances, and violent rebellion against the system. The most fundamental human drive to choose a partner, to build a family, becomes a function of the state, a cold variable in the mission's success. At what point does the human spirit break under such control? At what point do the inhabitants decide that the promise of a distant new world is not worth the price of their own souls? This is the fertile ground from which mutiny is born, but the most likely catastrophe is not a sudden violent uprising. It is a slower, more creeping decay, the decay of knowledge. The first generation are brilliant scientists and engineers. They understand every circuit, every line of code, every fusion process. They pass this knowledge down to their children who become apprentices. But knowledge is not a perfect heirloom. It frays with each transfer. By the 20th generation, the inhabitants might still know how to perform the maintenance rituals to keep the ship running, but they may no longer understand why they are doing them. The deeper principles of physics and engineering could be lost. The ship becomes a piece of ancient magical technology. Its operators are no longer scientists. They are priests chanting the litanies from maintenance manuals they cannot fully comprehend. What happens when a system fails that is not in the manuals? A crisis that requires not just rote learning but true innovation. The population stripped of its foundational scientific knowledge would be helpless. They would be a pre-industrial society living inside the decaying body of a technological god they can no longer understand, let alone repair. The ship, once a vessel of hope, slowly transforms. It becomes a tomb coasting silently through the void. Its internal lights flicker and die one section at a time. Its inhabitants huddle in the remaining warm-powered sections, telling stories of the great beginning and the golden age, when the ancestors commanded the sky and the metal walls hummed with life. The destination, a name in a forgotten language, becomes irrelevant. Survival day to day is all that remains. We can envision numerous paths to this collapse. Consider the solipsist heresy. After centuries, a charismatic leader emerges. They preach a new and seductive truth: there is no earth, there is no destination star. These are lies, fables created by the original masters to enslave the generations. The ship, they proclaim, is the entirety of existence. It has always been, it always will be. This heresy would be incredibly powerful. It offers freedom from the crushing weight of the mission. It validates the reality of the only world they have ever known. A civil war could erupt, a schism between the believers who cling to the mission and the solipsists who fight for the perceived truth of their metallic universe. A war fought with maintenance tools and salvaged equipment in the narrow corridors of a world tearing itself apart. Or consider a more subtle unraveling: the cultural drift. Language itself would evolve. Over millennia, the tongue of the first crew would become as alien as ancient Sumerian is to us today. The mission logs, the technical libraries, the cultural archives, all of it would become indecipherable. Humanity's legacy, the very reason for the voyage, would be locked away behind a barrier of unintelligible language. Customs would shift. New traditions born of the unique pressures of shipboard life would emerge and solidify. The concept of personal property might vanish in a resource-scarce world. The idea of privacy might become an obscene anachronism. The inhabitants of the starship after 200 generations would not be our cultural descendants. They would be an entirely new alien branch of humanity forged in the crucible of a completely artificial existence. If they were to finally arrive at their destination, these beings might be utterly unequipped to cope with it. The chaos of a real ecosystem, the weather, the wildlife, the open space, might be psychologically unbearable. They might refuse to leave the sterile, predictable safety of the ship. The womb that carried them across the stars would become the tomb that prevents them from ever touching a new world. They would have crossed the ocean only to die of thirst on the shore. This is the silent, terrifying argument against the Starship Ark. It is not an engineering problem. It is a human one. We are creatures of a specific context, a planet with a 24-hour day, a certain gravity, a complex biosphere, and open horizons. Our minds, our societies, our very biology are tuned to this reality. Take us out of that context for long enough, and we may simply break. We try to imagine a star-faring humanity as a triumphant extension of ourselves, brave explorers planting a familiar flag on new soil. But the reality is that the journey itself would change them into something we might not even recognize. The destination would not be reached by us, but by our distant shipborne progeny, a people whose psychology and sociology would be as alien as any extraterrestrial life we could hope to find. They would be a people for whom the memory of running in a field is a genetic fiction. A people for whom the sky is not a vast expanse of blue and black, but a domed ceiling with simulated stars. A people whose entire history is contained within a few kilometers of Hull, whose ancestors are every person they have ever met. We would be asking them to carry the torch of human civilization without ever allowing them to feel the warmth of the fire that forged it. We would be entrusting them with our greatest dream, while trapping them inside our greatest nightmare, a world without change, without frontiers, without escape, a perfect, ordered, and ultimately soul-crushing machine. So we are left with a sobering realization. We can design the vessel, we can plot the course, we can shield it from radiation and power it for eons, but we cannot engineer the human heart to endure the void. We cannot foolproof a society against the slow decay of purpose. We cannot quarantine a dream from the virus of despair. The ultimate challenge of interstellar travel is not overcoming the distance between stars. It is overcoming the distance between who we are and who we would need to become to survive the journey. And in that transformation, we might lose the very thing we were trying to save in the first place. Our humanity. Imagine a single coin. Now picture a stack of those coins reaching to the moon. That impossible tower of wealth is still not enough. It is a rounding error in the final budget for our escape. We have spoken of the crushing distances and the slow decay of time. We have confronted the silent fury of radiation. We have stared into the abyss of our own biology. We have considered the fragile human mind lost in the dark. But all these challenges converge on a final, intractable problem. A barrier built not of physics, but of sheer brute force logistics. It is the seventh and final reason we may never leave our galaxy. The monumental, staggering and soul-crushing cost of building a world, because that is what we are truly talking about. Not a ship, not a vessel, not an ark, in the simple sense. To survive for millennia between the stars, you cannot simply pack a lunch. You must pack an entire planet. You must construct from scratch a miniature Earth, a self-contained, self-repairing, self-sufficient biosphere. A clockwork world, sealed in a bottle and thrown into infinity, and the price tag for this bottle is the Earth itself. Let's begin with the blueprint, the sheer physical scale of this endeavor. Your generational starship would not be an elegant dart of science fiction. It would be a brute, a behemoth, a moving mountain of metal. Think of the largest structures humanity has ever conceived. The Great Pyramid of Giza, a wonder of the ancient world. Imagine 1,000 of them welded together. Take every aircraft carrier, every supertanker, every skyscraper on Earth. Melt them all down into a single colossal mass. You are still only scratching the surface of what is required. To house a viable population of several thousand souls, to provide them with agriculture, industry, and living space, to shield them from the hard radiation of interstellar space, you need mass. Unspeakable quantities of mass. Estimates place the minimum requirement in the tens of millions of tons. More likely it would be hundreds of millions, perhaps billions of tons. A new asteroid forged in the furnaces of human ambition. This is not a vehicle, it is a nation, state given wings. Where does this material come from? Trillions of tons of processed steel, aluminum and titanium, vast quantities of carbon composites, polymers and ceramics, kilometers of copper wiring, optical fiber and superconductors, precious caches of rare earth elements, platinum and gold, the vital ingredients for every circuit board, every medical device, every tool that will be needed for 1,000 generations. Could we mine it all from Earth? To do so would mean stripping our world bare. It would be an industrial cataclysm on a geological scale. the global mining industry working for a solid century, producing not for our civilization but for a different one entirely, one that is leaving. The environmental cost alone would be staggering. The economic upheaval would rewrite the story of our planet. It would be the single greatest undertaking in human history, and it would happen before the first engine ever ignites. Perhaps then we look to the heavens for our materials. We become masters of the solar system before we dare to leave it. We capture asteroids, hollowing them out for their metallic hearts. We establish industrial bases on the moon, refining its regolith. We build colossal manufacturing plants in the vacuum of space, constructing the ark piece by piece in the silence of orbit, an incredible vision of our technological maturity. But this only pushes the problem back one step. Building that interplanetary industrial infrastructure, that alone is a project orders of magnitude more complex than anything we have ever attempted. It is a multi-generational challenge in and of itself, and it is merely the prerequisite, the ticket to the real show. Let us assume we solve it. Through some miracle of unity and engineering, we build our world. It hangs there in the darkness, a testament to our will. Billions of tons of hope gleaming in the light of a distant Sunday. Now we face a problem of pure, unforgiving physics. The tyranny of the rocket equation, getting off the ground. Earth's gravity is a deep, powerful, and relentless well. To escape it requires a ferocious expenditure of energy. For every kilogram you want to lift into orbit, you need many more kilograms of powerful, explosive fuel. That fuel, in turn, has mass that also needs to be lifted, which requires even more fuel. It is a recursive nightmare, a spiral of diminishing returns. We have launched rockets weighing thousands of tons to place a payload of just a few dozen tons into orbit. Now apply that same brutal mathematics to our starship, a vessel weighing not thousands but billions of tons. The energy required to push it out of the solar system, to give it that first critical nudge towards another star, is difficult for the human mind to truly comprehend. It would be equivalent to a significant fraction of the entire annual energy consumption of our current civilization, not just for a day or a month, but for years on end. An unrelenting campaign of launches of fusion drives of beam propulsion, an energy expenditure that would make all other human endeavors pale. The economic cost of the fuel alone would be astronomical. The infrastructure needed for such a launch would blanket continents. We would have to fundamentally reorient our global economy, moving it from a model of consumption and growth to one of singular, obsessive, planetary scale focus, building and launching this one object. For generations, this would be our primary purpose. Our pyramids, our cathedrals, our moonshot all rolled into one. A project that consumes the present for a future no one alive will see. And still, we have only dealt with the shell. The real challenge, the true heart of the problem lies within. The creation of a perfect closed-loop life support system. A ghost of an ecosystem designed to function flawlessly. Not for a week-long mission to the moon, not for a year on a space station, but for millennia. For 100,000 years, perhaps more. This is where the task shifts from merely monumental to nearly divine, because what we are trying to replicate is the subtle genius of Earth, a planet-sized biological machine that has been refining itself for more than 3 billion years. Consider the air you are breathing right now. It is an intricate, perfectly balanced cocktail of gases, maintained by a global network of forests and oceans, a system so vast, so complex, so buffered by its own scale, that it can absorb immense shocks and still find equilibrium. On your starship there is no buffer. There is only the unforgiving mathematics of chemistry. Every atom of oxygen your descendants breathe must be generated, likely from vast hydroponic farms or algae-filled bioreactors. Every molecule of carbon dioxide they exhale must be captured, scrubbed from the air, and fed back to the plants. It must be a perfect, unbroken cycle, a cosmic pendulum swinging between animal and vegetable. But what if something goes wrong? A blight attacks the algae. A critical pump in the atmospheric processor fails. A subtle, unforeseen chemical contaminant builds up in the system. On Earth, a forest fire in one continent has little effect on the air. In another hemisphere, on the ship, a single failure point can mean total catastrophe. There is no outside to vent to. There is no fresh air. There is only the limited, finite supply of molecules within the hull. The margin for error is zero. A tiny, persistent leak in the system, losing just a few grams a day, becomes a fatal hemorrhage over the course of 1,000 years. The crew would slowly, imperceptibly begin to suffocate, their world's atmosphere bleeding away into the uncaring vacuum. Now think of water, the single most essential molecule for life as we know it. On Earth, it flows in a grand planetary cycle, evaporating from oceans, forming clouds, falling as rain, purified by soil, stone, and sunlight. On your starship, every single drop is more precious than diamond. It cannot be created, and it can never ever be lost. Every liter used for drinking, for hygiene, for agriculture, must be collected, processed, and purified with perfect efficiency. Wastewater, grey water, humidity condensed from the air, even the moisture in the breath of every crew member, it all must be reclaimed. The technology for this exists, of course. We use it on the International Space Station today. Astronauts drink water that was just hours before their own sweat, or part of a colleague's urine. It is a triumph of engineering, but it is designed to work for months, maybe years. Its filters need replacing. Its systems require maintenance. The parts arrive on regular resupply missions from Earth. In the interstellar void, there are no resupply missions. Your water reclaimer must function without fail. Without new parts, you cannot manufacture yourself for 10,000 years. A single, unfixable breakdown in the purification system, and your mobile world dies of thirst. This leads us to the greatest biological challenge of all: food. Sustaining a human population for centuries requires a robust, a resilient, and a profoundly complex agricultural system. You cannot simply pack enough protein bars. You must bring a self-perpetuating food web. This means farms, acres and acres of them inside the ship, illuminated by powerful full-spectrum lamps that mimic the sun, consuming vast amounts of energy day in and day out. But a farm is more than just seeds, water, and light. It requires soil, not just inert dirt, but a living, breathing microbiome. A complex community of bacteria, fungi, and invertebrates that break down waste and recycle nutrients. Creating this living soil is a science we barely understand on Earth. Replicating it in a sterile, artificial environment and keeping it healthy for millennia is a Herculean task. A single devastating crop virus, a bacterial blight, could spread through your contained farms like wildfire, wiping out a primary food source with no hope of replacement. You need biodiversity. You cannot rely on just 3 or 4 crops. A sudden genetic vulnerability could be an extinction-level event. You would need to maintain a vast seed bank, a genetic ark within the larger ark, and you would need pollinators, swarms of bees or other insects living out their entire species' history within the confines of a metal can. What unforeseen pressures would that place upon them? How would their evolution diverge in that bizarre environment? What if, after 1,000 years, they simply forget how to pollinate? The delicate dance between plant and animal broken forever. Your civilization would starve surrounded by beautiful sterile flowers. This whole intricate ballet of life and chemistry is predicated on one radical philosophical shift: the complete and total abolition of waste. In our terrestrial civilization, waste is something we throw away, out of sight, out of mind. In the interstellar arc, there is no away, there is only here. Every single thing must be part of the cycle. Every scrap of food, every piece of packaging, every worn-out tool, every dead skin cell, every fallen hair, every exhalation of breath, every drop of sweat, every bodily fluid, every corpse. Nothing can be discarded. Everything must be feedstock, broken down to its constituent molecules and reintroduced into the one and only system you have. It is the ultimate circular economy, a concept we struggle with on a planetary scale with near infinite resources. Now imagine perfecting it in a tiny, fragile bubble, where the penalty for failure is not pollution, but oblivion. Even if you achieve this biological miracle, this perfect self-sustaining ecosystem, you are still faced with the slow, inexorable decay of technology. The ship itself is a machine, and machines break, metal fatigues, wires corrode, seals crack, bearings wear down. Over a journey of thousands of years, everything will fail. Not just once, but many times. A starship cannot simply pull over for repairs. It must be its own self-contained industrial civilization. This means you cannot just bring spare parts. You could never carry enough. You must have the ability to manufacture any part you might ever need. From the most basic bolt to the most complex microprocessor, this requires a complete end-to-end industrial base. On board the ship, you need robotic mining craft to harvest raw materials from asteroids you might encounter along the way. Assuming you can find them in the desolate emptiness between stars, you need refineries to process those raw ores into pure metals. You need foundries, forges, and chemical plants to create alloys, polymers, and exotic materials. You need 3D printers of incredible sophistication, capable of fabricating intricate machine components. You need clean rooms and lithography suites to produce new computer chips, because the ones you launched with will be ancient history in a century and utterly useless in a millennium. You aren't just launching a crew, you're launching a culture of making, a whole supply chain from asteroid to integrated circuit, miniaturized and packed into a single vessel. The complexity is dizzying, but more daunting still is the preservation of knowledge. It is one thing to have the machines, it is another entirely to retain the understanding of how they work and how to fix them when they break. The blueprints for every system, the code for every program, the textbooks of physics, chemistry, engineering, and metallurgy, all must be preserved without corruption across 100 generations. Generations who will be born and die within the machine, who have never known Earth or gravity or an open sky. Will they retain the discipline, the curiosity, the scientific rigor to maintain a technology they did not create and may not fully grasp? Knowledge is more fragile than any machine. A single dark age, a generation that loses the thread, and the great ship becomes a tomb, its secrets lost forever. A miracle of engineering drifting silently dead in the water. And so we arrive at the final crushing weight, the foundation upon which all these other impossible tasks must be built, the economic and political will to even begin. What is the cost of this world ship? There is no real way to calculate it because the number is too large. It transcends our familiar concepts of money. It would not be billions or even trillions of dollars, it would be in the quadrillions, an investment that would dwarf the combined gross domestic product of the entire planet for decades, perhaps for a century. It would be the most expensive object ever created by a factor of thousands. Who pays for such a thing? No single nation could afford it, no corporation could fund it. It would require a planetary consortium, a unified global effort on a scale unprecedented in our history, an organization with the economic power and political stability to shepherd a century-long project from conception to launch. We struggle to agree on climate change treaties. We fight over borders and resources. Could our fractious, short-sighted species truly come together for a single glorious purpose and sustain that unity for 100 years? It seems unlikely. And what is the return on this unimaginable investment? There is no profit. There is no strategic advantage. The people who pay for it will never see it succeed. Their children will not see it. Their great-grandchildren will not see it. The ship will not arrive at its destination for thousands of years, long after the nations and ideologies that built it have crumbled to dust. You are asking the entire world to make an enormous, painful sacrifice, to pour its collective treasure, energy, and genius into a bottle and throw it into the cosmic ocean, with no guarantee it will ever reach a safe shore. You are asking one generation to pay for another's distant salvation, a generational contract of staggering proportions. This then is the ultimate barrier. It is the point where all the other challenges braid together into a single insurmountable cable of impossibility. The physics of distance demands a ship that can last for eons. The biology of survival demands a perfect closed ecosystem. The engineering of longevity demands a self-sufficient industrial base. And all of it, every last bolt, every last drop of water, every line of code, demands a resource investment so vast it would beggar the planet. It creates a profound and terrible paradox. To build the ship that can leave Earth, you must first build a utopia, a unified, technologically transcendent and far-sighted Earth. And if you have built such a world, why would you ever want to leave? Leaving our galaxy is not a matter of designing a clever engine or finding a way to suspend human animation. It is a problem of world building, of creating a life support system as resilient and complex as a planet's, of fabricating an industrial base as versatile as a civilization's, of fostering a society as stable as a species' entire history. It requires us to solve nearly every problem here on Earth first: poverty, war, scarcity, and short-sightedness. We must become masters of our own house. Before we can dream of building a new one among the stars, the starship is the ultimate test. It holds a mirror up to our species, and it reveals that the vast, cold emptiness between the stars is not the true barrier. The greatest gulf we must cross is the one within ourselves. Our inability to think on geological timescales, our struggle to act as one, our failure to see that the most complex machine we will ever manage is the one we are already living on. And if we cannot sustain this world, this Earth, we will surely have no hope of sustaining a tiny, fragile copy of it, lost in the great and silent dark. We have arrived at the end of a very long journey, a journey not through space but through the stark realities of physics. We have stared into the unbridgeable gulf that separates our galaxy from all the others, and we have asked a simple human question: can we ever cross it? The universe, in its silent, cold indifference, has answered. We have now examined the evidence piece by formidable piece. It's time to review the verdict, to assemble the final account of the 7 great barriers that wall us within our home galaxy, the 7 cosmic laws that declare the Milky Way our cradle and perhaps our final destination. First, we confronted the tyranny of sheer, unimaginable distance. The numbers are so vast they defy our intuition, rendering our maps of Earth, our solar system, utterly quaint. Andromeda, our closest major galactic neighbour, is not a destination. It is a 2.5 million year-long death sentence for any conceivable form of travel we can currently engineer. This is not an ocean to be crossed, but a void so profound that it swallows generations, empires, and the very memory of home. The abyss between the galaxies is a measure of cosmic loneliness, a silent testament to the universe's preference for separation. It is the first and most fundamental lock on our galactic door. A chasm so wide that light itself, the fastest thing in existence, becomes a weary pilgrim on its journey from one shore to the other. We are marooned on an island of stars, and the space between islands is an expanse of nothingness that beggars all human comparison. To contemplate this distance is to understand true isolation. Then we collided with the universe's ultimate speed limit, the immutable law of Albert Einstein that nothing with mass can ever reach the speed of light. It is not an engineering challenge to be overcome with clever design. It is a fundamental property of space-time itself, woven into the fabric of reality from the first moment of the Big Bang. As you approach this cosmic barrier, reality itself conspires against you. Time slows to a crawl and your mass swells toward infinity. The universe demands a boundless toll of energy for each tiny gain, a price that rises exponentially until it eclipses all the power our civilization could ever hope to command. Light speed is not a goal. It is a cosmic horizon, a boundary we can approach asymptotically but never ever touch. This law transforms the already staggering distances from a problem of time into a problem of fundamental impossibility. It is the universe declaring thus far and no farther. Our third barrier was the brutal economics of cosmic travel energy. To propel even a modest craft to a mere fraction of light speed requires an energy budget that dwarfs our planetary consumption. We are not talking about a better fuel or a more efficient engine. We are talking about harnessing the total output of stars, of commanding forces that forge elements in supernova explosion. The energy required for an intergalactic journey is apocalyptic, a bonfire of matter and antimatter on a scale we cannot comprehend, let alone control. Every plan, every hopeful design founders on this single colossal fact. We are creatures of low-energy chemistry living on a quiet world powered by a gentle, distant star. The physics of interstellar, let alone intergalactic flight, belongs to a different order of existence entirely. It's the energy of cosmic cataclysms, not the quiet work of biology. We simply do not have the currency to pay for such a voyage. The universe does not trade in dreams, it trades in jewels, and we are profoundly, unimaginably poor. Fourth, we faced the invisible storm of intergalactic radiation. The space between galaxies is not truly empty. It is a shooting gallery of high-energy cosmic rays, particles accelerated to nearly the speed of light by black holes and exploding stars a billion years ago. Our planet's magnetic field, our sun's solar wind, they form a tiny, fragile bubble of safety in the Milky Way. Outside this sanctuary there is no shield. These particles are not like the radiation we know on Earth. They are atom-sized bullets that would shred our spacecraft, corrupt our computers, and tear apart the very DNA of any living thing audacious enough to venture there. To survive, this unending bombardment would require shielding so thick, so massive, it would make the energy problem even more grotesquely impossible to solve. The void is not benign, it is lethal. It is a realm of pure, unfiltered cosmic violence, and we are built for the gentle quiet of a sheltered world. This led us to our fifth great wall, the prison of our own biology. We are fragile, intricate machines of water and carbon, perfected by 4 billion years of evolution for one specific planet. Our bodies are tuned to its gravity, its atmosphere, its 24-hour cycle. We are creatures of a certain time scale. Our minds and bodies decay. We are designed for a handful of decades. A multi-million-year journey is not something we can endure. Our psychology would shatter in the unending isolation of the void. Our biology would crumble under the dual assault of radiation and the slow, insidious decay of zero-gravity existence. Even fantastical ideas like suspended animation or generation ships run into the fundamental problem of decay and complexity. Systems fail, information corrupts, and life over such timescales finds a way to fall apart. We are ephemeral beings, sparks that flicker for a moment. The cosmos operates on a clock whose ticks are measured in eons. Our mortal flesh is simply incompatible with the scale of our dreams. Sixth, we encountered the silence of the information horizon. Imagine a vessel 1,000,000 years out hurtling toward Andromeda. How do you speak to it? A question sent from Earth would take 1,000,000 years to arrive. The answer another 1,000,000 years to return. Civilizations would rise and fall on Earth in the time it takes to have a single, simple exchange of information. The crew would be utterly, irrevocably alone. There could be no guidance from home, no help, no shared discovery. The connection would be severed by the sheer geometry of space-time. They would not be an extension of humanity, but a new, isolated species forever cut off from their origin. Exploration without the ability to communicate, to share, to return knowledge is arguably not exploration at all. It is simply exile. The light speed limit is not just a barrier to travel. It is a barrier to conversation, to community, to shared existence. It enforces a solitude so absolute it defies our social nature. And finally, we faced the most profound barrier of all. The unnerving reality that the universe itself is expanding, and this expansion is accelerating. We are not just trying to cross a static gulf. We are trying to swim up a waterfall that is growing faster every second. Beyond a certain point known as the cosmic event horizon, galaxies are receding from us faster than the speed of light. The very space between us and them is being created so rapidly that no signal, no ship, no matter how fast, could ever reach them. They are not just far away in space, they are disappearing from our future. They are falling away from our reachable universe forever. This is the ultimate checkmate. The cosmos is not merely vast and difficult to cross. It is actively pulling itself apart, isolating its island galaxies in ever deeper pockets of unreachable, unknowable darkness. We live in a moment, a precious fleeting epoch, where we can still see these other galaxies, but the window is closing. The journey is not just becoming harder, it is becoming impossible. So there they are. The 7 great seals on our galactic home: distance, speed, energy, radiation, biology, information, expansion. Each one on its own is a formidable challenge. Together they form a fortress wall of cosmic law, a statement from the universe about the limits of mortal ambition. It is easy to hear this verdict and feel a sense of failure, a sense of confinement, of being trapped. Is humanity destined to be a single planet, single galaxy species? Is this magnificent vessel, the Milky Way, not a ship but a cage? Perhaps we have been asking the wrong question all along. Perhaps the desire to physically leave, to plant a flag on a world in another galaxy, is a profound misunderstanding of our place and a failure of our imagination. Is the ultimate goal of a species to spread its physical body? Or is it to spread its understanding? What if the insurmountable barriers are not failures but guideposts? What if they are the universe's way of redirecting our focus, of forcing us to reconsider what true exploration really means? Maybe the great human adventure does not lie out there in the cold, empty and lethal chasm between the galaxies. Maybe it lies in other directions we have only just begun to chart. Perhaps the next great frontier is not outward, but inward. Inward into our own solar system, a realm so rich and diverse that we have barely scratched its surface. We have spent decades sending probes, our robotic emissaries as our eyes and hands, into these alien realms, and what they have shown us is a universe of wonders right here in our own cosmic backyard. Imagine a new golden age of exploration, not with fragile human bodies, but with fleets of sophisticated, intelligent machines. Imagine robotic explorers descending through the thick nitrogen haze of Titan to sail upon its liquid methane seas and explore its hydrocarbon shores. Imagine cryobots powered by nuclear hearts designed to burrow through miles of solid ice on Jupiter's moon Europa, to deploy autonomous submarines into its hidden global ocean, an ocean that may have held life in utter darkness for 1 billion years. These are worlds of profound mystery and scientific revelation. Imagine missions to the metallic heart of a shattered protoplanet, the asteroid Psyche, a journey to the core of a world we can never visit. Imagine landing on the chaotic cantaloupe terrain of Triton Neptune's strange captured moon, with its ice volcanoes belching nitrogen frost into a razor-thin atmosphere. These robotic avatars could be our proxies, our senses extended across millions of miles, sharing their discoveries in real time. They would be tireless, immortal explorers, immune to radiation, unburdened by the fragile needs of flesh and blood. Through their cameras, we could stand on the scorched surface of Mercury. Through their drills, we could analyze the ancient soil of Mars. Through their spectrometers, we could taste the atmosphere of Venus. This isn't a lesser form of exploration. It is a more profound, more sustainable, more intelligent form. It is the act of a species that has learned to see with more than its eyes and to touch with more than its hands. The solar system is not a stepping stone we must leave behind. It is a vast, complex and beautiful laboratory, an heirloom of cosmic history with enough mysteries to occupy humanity for 1,000 generations. To truly know it would be a triumph. And there is another frontier, one we often overlook in our rush for the stars. It is the most complex, dynamic and beautiful object we have yet discovered anywhere in the universe, our own planet. We dream of terraforming Mars, of bringing life to a dead world, while we are systematically dismantling the intricate workings of the only living world we know. Perhaps the greatest challenge humanity will ever face is not conquering the void, but mastering the art of living here, of understanding the deeply interwoven systems of our own biosphere, the delicate dance between geology, atmosphere and life that has allowed us to exist. This is a frontier of immense complexity. To reverse the damage we have done to create a truly sustainable civilization that lives in balance with its planetary host is an engineering and scientific challenge far greater than building a simple starship. It requires a deeper understanding of our own nature, of our societies, of the very essence of what it means to be an intelligent technological species. To secure the future of life on this planet, to preserve the library of 4 billion years of evolutionary genius stored in its DNA, is not a consolation prize. It is the prime directive. What is the point of dreaming of other galaxies if we cannot preserve the one cradle of consciousness we are sure of? The true mark of an advanced species may not be its ability to travel, but its ability to endure, to create a lasting and harmonious home. Earth is not our starting point. It is our masterpiece, and our work on it has only just begun. Finally, there is a third great adventure, one that requires no travel at all. It is the exploration of the cosmos, from right here, from within the confines of our galactic home. We have built extraordinary instruments, telescopes that are in a very real sense time machines. When the James Webb Space Telescope gazes into the deepest fields, it is not just looking across space. It is looking back 13 billion years into the past, witnessing the birth of the very first galaxies. These are shores we can never physically visit yet. We can see them. We can analyze their light, understand their chemistry, and watch them be born from the lingering fire of creation. Our telescopes are our true starships. They travel at the speed of thought, unconstrained by the laws that bind matter. Through them we can witness stars being born in pillars of gas and dust. We can watch them die in spectacular supernova explosions. We can detect the subtle wobble of a distant star and deduce the presence of a planet, a new world orbiting it. We can even taste its atmosphere from hundreds of light years away. And we can listen. With radio telescopes, we scan the heavens, listening for the whispers of other intelligences, a search that is in itself one of the most profound quests we have ever undertaken. The human mind, armed with mathematics and the scientific method, has journeyed to places no ship ever could. We have plumbed the quantum realm and the interior of a black hole. We have mapped the cosmic microwave background, the echo of the Big Bang. We have conceived of dark matter and dark energy, the invisible scaffolding and engine of our entire universe. This is the ultimate exploration. It is the universe itself, through us, becoming aware of its own grandeur. The quest for knowledge, for pure understanding, is an infinite frontier. It requires no fuel, no shielding, only our insatiable curiosity and the courage to confront the deepest questions. So we find ourselves back where we started, gazing up at the night sky. But our perspective has changed. The 7 barriers are not a judgment. They are a lesson. They teach us humility. They teach us to value what we have. They teach us to redefine our ambitions, to look for the infinite, not just in the expanse of space, but in the depth of our knowledge. The Milky Way is not our prison. It is our garden, our sanctuary, our grand and beautiful arena. It contains 400 billion stars, trillions of planets, countless nebulae, ancient star clusters, and a supermassive black hole of unimaginable power at its heart. It is a place of breathtaking beauty and endless mystery. We are not its prisoners. We are its children. We are the momentary consciousness of this vast, spinning island of light. To spend our existence charting its wonders, understanding its history, and securing the future of its one-thinking species is not a limited destiny, it is a privilege. Perhaps the greatest journey is not to leave our home, but to finally, truly, for the very first time arrive here, to understand it, to cherish it, and to recognize the sheer staggering miracle of our existence within this magnificent river of stars we call our own.